Voice coming.
Sir, is it audible now?
Yeah, you are audible, Niranjan.
Very good morning to all of you. Myself, Dr. Niranjan R.S., working as an assistant professor in the Department of Physics, and also I am working as an IQSC coordinator. I would like to welcome Dr. K.M. Ishwarappa sir, Associate Professor, Department of Physics, Davangere University, on behalf of our college and also on behalf of the organizing committee. I welcome you, sir.
Thank you, Niranjan.
On behalf of the organizing committee and also on behalf of our college, I welcome our college principal, Dr. Dinesh K.S. sir. Dinesh K.S. sir, I welcome you, sir. And also, I would like to welcome our college physics department HOD, Nandakumar sir, and he is the convener of this program. I welcome you, sir. And Harshavardhan sir, convener of this our science forum and HOD department of mathematics. I welcome you, sir, for this state level webinar. And also, I welcome our technical assistants, Kannada department, Professor Sundaresh sir. Welcome you, sir. And also, I would like to welcome our department faculties, Yashwant sir, Divya Bharati madam, and others. And also, I would like to welcome all the participants and the faculties who supported and for this organizing this webinar. And I request now Ishwarappa sir to continue the session. Now I request Ishwarappa sir to continue the session. Over to Ishwarappa sir now.
Thank you very much. I request organizers to mute the mutes of the other participants.
Please, all the participants, please mute your audios. All the participants, please mute your audios.
Let me share the window. Okay, so is PPT visible, Niranjan?
Yes, sir, visible, sir.
Okay, right.
PPT is not visible.
PPT is visible now?
Sorry, you are visible, but PPT. Yes, sir, visible.
Okay, right. I am in the first slide.
Yes, sir.
Okay. 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 Uh, First of all, let me congratulate organizers for organizing a state level webinar. And this type of interactions are good in an academic, developing the academic environment in any academic institutions. So let me let me express my sincere thanks to the organizers for being invited me to deliver a talk on novel composite materials for nuclear radiation shielding. So before going into the actual the material aspect for radiation shielding, let me explain, because it seems most of the audience are the students from the BSc, possibly some faculty also participating in this. See, here the many different radiations, for example, alpha, beta, gamma, neutrons. So we need to know their penetration power in different materials before applying a particular material for shielding. So one should know what is their penetration power in different material. So for example, alpha particles, so we can see here, we can stop this alpha particle using a thin sheet of paper, right? All of you know this during your BSc classes itself. We know that we can stop this alpha particle using a thin sheet of paper because its stopping power, because of its heavy mass, due to its heavy mass of the alpha particle, so its stopping power of any material is very, very high for alpha particle. And as per the beta particle, so little smaller particle, smaller size, and having a charge, unit charge, it can penetrate easily through the paper, sheet of the paper, and it can also penetrate through our tissues. A moderate energy electron beam can pass through our tissues. We can stop these electrons using some certain thickness metals, like copper, things like that. So neutron, so it's a peculiar particle, so we cannot stop. So I will tell you the peculiarity of the neutron later. See here, the neutron can be stopped. We cannot stop using the paper. We cannot stop using the metal. We cannot stop this neutron using the lead, right? So but the peculiarity of the neutron is that we cannot energy neutron. I mean, say 2 MA is stopped with some 2 inch. And as for gamma, again, particle is to butter and but it can be stopped using some sort of IZ material like the water or any low material. The electrons and gas gamma, it depends upon the atomic number of the observer, whereas here the neutron cannot be stopped using the lead, though its atomic number is very, very high. The attenuation of the neutrons depends upon the Z again, but that should be very, very low, right? So because neutron lose their energy rapidly in the low Z material through scattering absorption, whereas the neutron will not lose their energy. How we can stop using the water, some sort of hydrogenous material. Even concrete is also good shielding for gamma, though it contains some Z material. Concrete is also contains some low Z material, so concrete is gamma also. Right, with this, before let me move to the next slide, which tells that what are the, very broadly it talks about why we need radiation shielding. See, radiation shielding means if you expose to any ionizing radiations, even non-ionizing radiations like neutron, that could be a biologically hazardous to both humans and the for environment, or even for some devices wherein components are there, electronic components are there. So the exposure to these radiations leads to, in the case of human beings, it may lead to the organ damage, some sort of a cell mutations, or if it is exposed to some electronic devices, there can be a component failure or some other harmful effects. See, these pictures in the slide shows that this is a radiation-induced lung, right? I mean, injury. Lung got injury due to the exposure to some sort of radiations like coma. And the radiation exposure, I mean, continuous exposure of radiation can also lead to the cancer and uncontrolled growth of the cells. A mutation can be produced because this mutation can be produced by ionizing radiation. So this schematic diagram shows how this radiation could cause the radiation. It breaks this chromosome chain, and it breaks the micronucleus, and it forms a separate cell. Then there can be a uncontrolled growth of the cell, so it leads to the tumor. So for these things, in order to avoid this radiation damage to the tissues or component failure in the electronic devices, and some other advanced applications also need some advanced shielding material also. So let us go for some brief about what are the existing shielding materials and what are the future requirements as far as the radiation shielding is concerned. See, for example, inevitably we need to use the radionuclides, because these radionuclides which emits radiations are found applications in many fields like industrial, wherein these radiography, imaging of the metal casting in order to find the defect during their formation, right? During when they form the metal, so in order to detect any defects in that, even airline defects may cause the devastating effect, especially in the case of aviation industry. If the aeroplane blades are made with even if a minute thin airline fracture is there, it can lead to the devastation. So in order to avoid that, one has to detect during the preparation itself, we need to detect the defects. So that could be possible using this radiography, right? And also in the medical imaging, also we are using the radionuclides. So we are inevitable to expose to these nuclear radiations. In agriculture also we are applying these radiation for development of ripening, degree of control the ripening, and also increase the shelf life of the fruits, vegetables. People are using the food degradation techniques. So there also we need to very careful in exposing the radiations, and it needs some radiation shielding materials. And of course the space applications wherein all our electronic devices are prone to expose high radiation level at a higher altitude. So for these, what are the traditional shielding materials? These shielding materials they're generally costly and heavy and often toxic to the environment. This, for example, this lead and other are very toxic material that needs advanced shielding materials are nuclear medical imaging and therapy, and nuclear waste storage, and space explorations, and energy physics experiment. So therefore, there is an increasing demand for developing a new radiation shielding material that can attenuate both gamma rays and neutron while mitigating the disadvantages of traditional shielding materials such as lead and concrete. See here, the requirement is mainly the shielding material for a mixed radiation field, for example, gamma radiations and neutrons, something like that. So, cutting edge research replacing these toxic radiation materials like lead and others continuously is underway. So, with this, now let's go for some basics. Very briefly, I'm going to the basics, how this radiation gamma particularly interact with the material. So that based on these interactions, one can decide what is the material to be used for the shielding of these radiations. All of you maybe have read that these gamma radiations interact with the matter through three important mechanisms or processes. That is, one is photoelectric effect, second one is Compton scattering, third one is pair productions, right? And all these processes lead to a partial or complete energy transfer of these energy gamma radiations. And each of these processes associated with the corresponding cross sections. Cross section means probability of a particular interaction take place. What is the probability that photoelectric interaction take place in a particular gamma energy in a particular absorber or specific Z value. So the total total cross section will be equal to the sum of the partial cross section, that is sum of the photoelectric cross section, Compton scattering cross section, and pair productions. See, if I want to look into the relative contribution and in the energy range in which these effects are dominant, or these effects are more effective, or what is the energy range these effects are more effective. So this picture, this particular graph clearly shows that the the Compton scattering is concerned, it is more effective above 400 kV and below some 10 MeV. And at higher energy range, the pair production is very dominant, right? So this picture very clearly tells about the dominance of the different process, energy range in which these different processes are dominant. And see, now let us see how the gamma ray attenuation is happening in a particular absorber. So based on the definitions of interaction cross-section, that is photoelectric cross-section, Compton scattering cross-section, and pair production cross-section, the definition of cross-section is, it is an effective area represented by a particular absorber nuclei to the incoming beam. Effective area. It has having the dimension of area. So it is nothing but what is the probability the beam intensity beam interact with the material, and what is the probability that a particular number of photons or particles are removed from the incident beam. That particular probability is what is known as it is a measure of cross section, or what is known as a cross section, right? Suppose if monoenergetic gamma rays are collimated into a narrow beam, right? And if the detector is placed behind the material, and it only detects the gamma ray that pass through this absorber. Out of this number of photons, some of the photons are removed as a result of the various interactions, right? So obviously it should be actually it shows that exponential dependency of the attenuation of gamma rays can be shown in this figure. So each of these interactions removes various, photoelectric Compton pair production removes the photon from the beam, either by absorption or by scattering away from the detector. Therefore, interaction can be characterized by fixed probability of current per unit or the total attenuation and the Compton effect and the wave production. Total attenuation coefficient will be equal to the sum of the attenuation coefficient due to all this process. So for intermediate energy, so and the cross section in the intermediate radial energy coefficient will be almost independent of the observer. It is almost same for all the different observer, because of Z by A is a constant. Whereas at small values of gamma ray energy or high values of gamma ray energy, so this attenuation coefficient is depends on the high powers of atomic number. For example, for the photoelectric effect, the cross section is proportional to the Z to the power of 5, and for a wave production, the cross section is proportional to the Z square. So it is high power proportional to the high powers of Z at higher and smaller values of energy. And the intermediate energy, so it is independent of the observer. So if suppose your observer consists of a mixture, for example, if it is an alloy, say for example brass is an alloy of copper and zinc. So in that case, how to find the attenuation coefficient? So we need to use a mixture rule. The mixture rule is given in this equation, wherein mu m, mass attenuation coefficient, is equal to, so the sum of the attenuation coefficient of all the materials, wherein we need to take the effect of this weight fraction. Suppose in the copper and zinc case, if it is 60% copper and zinc 40%, then the weight fraction is 0.6 and the 0.4. Multiply the corresponding mass attenuation coefficient of copper and the mass attenuation coefficient of zinc, then you will get a total mass attenuation coefficient for the mixture. So this is what is in the mixture rule. So now let's go for what are the parameters one can look while deciding the material for a radiation shielding. So what are the different parameters we need to evaluate before using the particular material for radiation shielding? There are various parameters which decides the effectiveness of the material for radiation shielding. The first one is the linear attenuation coefficient of the material for a particular radiation, and mass attenuation coefficient. Mass attenuation coefficient can be obtained just by dividing the linear attenuation coefficient by density of the material. And the third important parameter to decide the material effectiveness for shielding is the mean free path. Right? It's a mean free path. And the next one is off value layer, radiation protection efficiency. And sixth one is the exposure build-up factor, energy absorption build-up factor. These are the very important radiation shielding factors one has to evaluate for any material for using as radiation shielding material. Let us discuss one by one. See, linear attenuation coefficient, as you know, this simply can be obtained with the concept of B-Lambert's law, that is I is equal to I naught to t power minus mu x, where I is the intensity of the radiation in a particular absorber, and the incident intensity, and of course mu is the linear attenuation coefficient, which has a dimension of centimeter inverse, and x is the physical thickness of the observer. So there are two main features of the linear attenuation coefficient. What are those? Linear attenuation coefficient increases as the atomic number of observer increases, and linear attenuation coefficient for all the material decreases with the energy of the gamma rays. At the higher is the energy of the gamma ray, the attenuation coefficient decreases. Because the higher is the energy, it can easily penetrate into the material. Then second important right? So rho t, after multiplying with the density for the B-Lambert's law, then you will get a mu by rho into rho t, where rho t the rho into 3 the mass thickness, and this unit is mass. The mass attenuation coefficient unit is centimeter square per gram, whereas the rho into thickness unit is gram per square. That's the margin. And the another important parameter is the mean free path. Mean free path is defined as an average distance traveled by a photon before being observed in a particular medium. So, what is the average distance traveled by radiation before it completely stopped in the material? So, this is what is known as mean free path. Mean free path is inverse of the linear attenuation. That is mean free path equal 1 over mean or mu inverse. And the fourth one is off-value density. Initial intensity. For example, if I the intensity after passing through that observer, it should be equal to 0.5 I naught, where I naught is the incident intensity. If I naught reduces to I naught by 2 for a certain thickness of the material, that thickness is what is known as off-value layer or off-value thickness. This off-value thickness or layer decreases as the atomic number of observer increases. I mean, the off-value thickness is, decreases for a high Z material. For example, see, 35 meter of air is needed to reduce the intensity of a 100 kV gamma ray beam by a factor of 2, whereas just 0.12 millimeter of lead can do the same thing. Means the 0.2 millimeter of lead is enough to reduce the 100 kV gamma ray intensity to its off initial value. So therefore, the off-value layer for all the material increases with the energy of the gamma rays. For example, 0.26 centimeter for iron at 100 kV to about 1.06 centimeter at 500 kV. For the same iron, it is only 1.06 centimeter at 500 kV. So this shows that off-value layer increases with the energy of the gamma ray. So let me speak on this validity of this exponential law. Means how long this attenuation law I is equal to I naught in t power minus mu x valid. See, the exponential law will always describe the attenuation of primary radiations. If secondary particles are produced, or if the primary radiation changes energy or a direction, then the effective attenuation will be much less. This I is equal to I is equal to I naught in t power minus mu s is applicable only for a primary radiation. During the passage through a matter or during interaction through a matter, if the secondary radiations are produced or if the radiation changes its energy, then the effective attenuation will be different. It will be much less. Radiation will penetrate more deeply into the matter if the secondary radiations are produced, and if the radiation changes its energy, hence it can deeply penetrate into the material than as predicted by the exponential law alone. So this effect must be taken into account while evaluating the effect of a radiation shielding. For example, this figure clearly explains that see, the primary particle go on decreasing and the depth of the material increases. See, whereas the secondary particle produced during interactions it increases and reaches the maximum, again decreases in the higher depth. So if you take the all particles, it continuously decreases as the increases. So this build-up factor we need to take into account while deciding the shielding effectiveness of the shielding of a particular material. So now let us see what do you mean by a build-up factor. Build-up factor is an important parameter in distribution of photon flux in every object. Build-up factor is a correction factor that considers the influence of the scattered. If we just apply the exponential attenuation law, it won't take it. The scattered radiation. Here, scattered radiation is in the medium during shielding calculation. If you want to account for the build-up factor of the secondary radiation, then we have to include the build-up factor into your shielding calculation. So therefore, this build-up factor is a multiplicative factor which accounts for the response to the uncollided photons so as to include the contribution of the scattered photons. Therefore, build-up factor is defined as the ratio of total detector response to that of unscattered photons. So if you place a detector, so detector will give some response and divided by that of the unscattered photon, that what is known as build-up factor. So therefore, build-up factor is a function of gamma and a scattered photon divided by primary photon. If this B is, if there are no scattered photons, suppose the material, if there is no scattering, then B is equal to 1. So it will be same as that of your regular attenuation law. And if there are scattered photons, B will be greater than 1, right? Okay. So build-up factor data is the basic requirement for thermal calculation commonly used in shielding design. So actually it has been classified into two categories. There are two build-up factor expressions. One is energy absorption build-up factor. Second one is exposure build-up factor. What do you mean by energy absorption build-up factor? Energy absorption build-up factor, the quantity of interest is absorbed or deposited energy in the material. Energy or and deposited in the interacting material, and the is the absorbed response. Whereas in the case of exposure build-up factor, quantity of interest is the exposure only. Here the detector response function corresponds to absorption in the air, right? Whatever response is corresponds to absorption in the air. Whereas in the case of energy absorption build factor, it's a function that absorbs the interacting material. That's the main difference. So here in the exposure domain, as positive for the air, exposure is equivalent to the absorbed dose in the air. Otherwise, it will be different. Okay. So now with this background, detailed discussion of the various shielding parameters. Now let us move on to the actual shielding materials, and recently the recent development in radiation shielding material. So people have tried several. People have been trying effective radiation shielding material for both. Individually for the gamma radiation or neutron radiation, and also nowadays, especially in the case of accelerator and particle accelerator environment, wherein one can expect some mixed radiation. That can be a production of neutrons and in associated with the charged particles and the gamma radiations, where there is more chance of exposing to the mixed radiations, right? So for that, people are trying to develop a composite materials for these radiation shielding. See, we know that concrete has been formed from the loosely compact mass of small fragments or particles. Concrete is then a traditionally used material, and currently is also being used in the radiation environment. It has several limitations to be used as a shielding. What are the limitations? Due to its non-transparent characteristics, concrete is not non-transparent. It is not a transparent. So it is not possible to observe or monitor the internal environment. Suppose you wanted to know what exactly happened inside that radiation field where this concrete is used for the shielding. So it is not possible to see that. It is not possible to observe. And moreover, variation in the water quantity in the concrete often exhibit unwanted fluctuation in the attenuation because the water content in the concrete. So where this concrete has been used, sometimes there will be variation in the water quantity. So there is a fluctuation of attenuation in the attenuation coefficients. To overcome these limitations, so people have tried with several glass-based materials and which are having advantage that being transparent, so one can observe or monitor the internal environment in the radiation field, and these glass properties can be modified by changing the components and preparation methods. So people have developed various glass-based radiation shielding material, and people have studied the gamma ray attenuation parameters in the various glass-based shielding materials such as bismuth borate glasses, lead borate glasses, lead fluoroborate glasses, bismuth borosilicate glasses, alkali borosilicate glasses, barium borosilicate glasses, calcium strontium borosilicate glasses, lead silicate glasses, lead barium phosphate gases, etc. So attenuation parameter, studying the attenuation parameter of these glass-based composites reveals that these are the great potential, having the great potential to shield ionizing radiations like gamma radiations in any nuclear radiation environment. And people have also tried to synthesize a polymer nanocomposites for radiation shielding. These are the days people are trying with a nano. For any field, people are trying with a nano. So here in the radiation shielding, also people have tried developing polymer nanocomposites for radiation shielding. So over the last years, polymer nanocomposites have been considered as novel materials in many fields because of their outstanding special physical and mechanical features by adding only a small amount of nano reinforcements. See here in this case, nanocomposites for radiation shielding, polymer composites filled with nanoscale metal oxides, nanoscale metal oxides for radiation shielding, especially for the low energy X-rays, some 150 kV X-ray. So wherein these composites are very effective. People have tried and studied the radiation shielding parameter for low energy radiations. See here, these composites are containing matrix part and reinforcement part. Polymers are lightweight, non-toxic and flexible materials, and the chief advantage of using the polymer is their ability to process very quickly and their excellent chemical resistance. So yes, here the polymers have been used as a matrix part. And what about the reinforcement part? Yes, the nanoscale metal oxides and metal nanoparticles are the reinforcement phase. So these mixture of these two form a composites. And moreover, these polymers are having the low atomic number. As I told you, the gamma radiations shielding is more effective if it is IZ, right? But these polymers are having the low Z materials. So because as usual, the basic will be remain same. Higher is the Z, more is the attenuation for gamma radiation, and higher is the Z, least is the attenuation for neutron radiations. IZ material that have been considered as the alternative for lead and having nearly the same effects on the shielding gamma radiations are mainly high density with high atomic number, such as tungsten oxide can be used, bismuth oxide and barite oxides. See, you can see in the table that bismuth oxide has a higher lead is 11.34. So we don't want to use the lead because of toxicity. It's more hazardous to the environment. We need to go for a non-lead based radiation shielding material. Non-toxic is a much more critical issue, right? So therefore, we need to go for some non-toxic material like bismuth oxide for equivalent shielding effective based on lead. They are comparing with the lead. So how do you calculate it? The shielding performance was presented based on the lead equivalent. Lead equivalent is expressed in the units of millimeter of lead. Means whatever the growth you have used, see it is equivalent to one thickness of lead. That is what we are presenting here. The lead equivalent is given as which is equal to FPP is equal to performance is equal to attenuation coefficient of a fabric divided by attenuation coefficient of lead into the thickness of the fabric. The lead equivalent FPB on the shielding factor can be expressed as the correlation between the thickness D of the shielding fiber and the linear attenuation coefficient of tungsten and barium sulfate and the linear attenuation coefficient of the lead. So this formula will help in calculating the shielding performance lead of these fabric related to the lead. So they have demonstrated that cloth manufactured using the tungsten composite fabric and PET fiber fabric containing the barium sulfate can provide shielding from low dose radiation with 0.018 mm lead and 0.03 mm lead, which means that they can provide the equivalent radiation shielding also, which is provided by the lead, 0.18 and 0.03 millimeters of lead. So, and the advantage here is that manufactured cloth is a lightweight, does not interfere with the work-related activities. So we can wear as regular cloth. Such a clothing is of significant importance because these aircraft flying at higher altitude are exposed to the elevated level of natural cosmic radiations, as I mentioned earlier. This clothing may also find use in other industries such as medical, mining industry also, where they are prone to expose to the radiations from the material in the deep earth crust, where they can expect some sort of a radon gas, which emits alpha particles or some other gamma radiations also, where mining people also need this type of clothing because that provides the comfortable during the working environment, at the same time radiation shielding also. So you can see their performance, shielding performance. See, for an 27.7 kilo electron X-rays, barium sulfate containing fabric, the shielding is around 0.18, and where tungsten composite iron fabric is 0.03. So these are the percentage, shielding rate, 72%, tungsten is 83% for this particular 27.7 kV. So like that, and the energy increases, of course, as I mentioned, the shielding is also rate is also decreases. But in either the case, the barium, both the fabrics are providing the effective shielding. So our own group we also worked on some composites, bismuth-based composites. We have used the matrix as an HDPE, high density polyethylene, and we have studied with mixing the various quantity of bismuth oxide, but it's not an nano bismuth oxide, it's ordinary bismuth oxide. You could able to find the experimental, and you could able to measure the attenuation coefficient, both attenuation coefficient, mass attenuation coefficient, and other shielding parameter. I have just mentioned only the mu m, mass attenuation coefficient for our composites, HDPE plus 10% of bismuth, HDPE plus 20% of bismuth, HDPE plus 40%. So we can see here the HDPE plus 40% of bismuth composite provides a very, very effective shielding for the gamma radiations of 59.4 kilo electron volt. These radiations are emitting from the americium source, right? So we have also compared these with some theoretical calculations using XCOM and CNP. CNP is the main Monte Carlo calculation method. So these results are very, very good agreement with the experimental values. So with this, I'm going to end my talk. So if you have any questions, you can ask the questions. I request organizers to, if any question posted in the chat box, you can also read out. Now I'm ready to answer the questions. Over to Niranjan.
Thank you, sir. Thank you very much for your very nice presentation and very prolonged presentation. And we give the complete detailed information about the production materials from the radiation. And I heard that
yes, so particularly cloth made, because we cannot use the lead and other things for manufacturing. As I said, they are very toxic, and also we cannot make the yarn out of this lead. Tungsten, you can make the tungsten yarn or a fiber using the tungsten. So hence obviously because of the high Z of the bismuth, right, barium sulfate, which is similar to our clothing material, so definitely they are very effective in providing the shielding for low energy radiations. Particularly these are very useful in industry like aviation and medical imaging, wherein they are but generally use the low energy radiations.
Thank you, sir. Any more questions from the student side or from the participants? If you have any questions, please ask now. Sir is here. He will clarify the queries. Which is the best material, sir? Now in recent days, the nano composite material is best one, or an ordinary material is the best one in case of bismuth?
No, actually, see, what we have observed in the literature is because we have started to prepare the nanomaterial based radiation shielding material. We have not yet tested. We have prepared the ordinary bismuth oxide composites. And what I read in the literature, particularly this paper like this, what I mentioned here, these nanoparticles are providing a more effective shield than the ordinary, macroscopic particles oxides, because of their at the nanoscale, they show very high density. They also get improved, So in a sense, it's better to use nano-based composite materials for radiation shielding, owing to their advantages.
You told that, sir, China has published one paper in the Nature. That is also based on this same nano.
Yes. So we can see here this particular material. Made from tungsten composite fabric and PET containing barium sulfide. The both are providing the effective shielding. I'm sure that the shielding effectiveness is 0.018 and 0.03. So it's really they're having advantages, and they provide above all they provide a very comfort in their daily activities. In addition to providing the radiation shielding.
Okay, sir. Thank you very much, sir, for your informative speech, and I request our college principal, Dr. Dinesh sir, deliver the presidential speech.
ಬಹಳ ಸಂಪದ್ಭರಿತವಾದಂತಹ ಉಪನ್ಯಾಸ ಕೊಟ್ಟಂತಹ ಈಶ್ವರಪ್ಪ ಸರ್, ಇದನ್ನು ಆರ್ಗನೈಸ್ ಮಾಡುವಂತಹ ನಿರಂಜನ್ ಸರ್ ಅವರೇ, ಹಾಗೂ ಈ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಭಾಗಿಯಾಗಿರುವಂಥ ಎಲ್ಲ ಪ್ರೀತಿಯ ವಿದ್ಯಾರ್ಥಿಗಳೇ, ಆಸಕ್ತರೆ, ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. ಬಹುಶಃ ಈಶ್ವರಪ್ಪ ಅವರು ಒಳನರಸೀಪುರ ಕೋಯೆಡ್ ಕಾಲೇಜಲ್ಲಿ ಬಹಳಷ್ಟು ವರ್ಷ ಸೇವೆ ಸಲ್ಲಿಸಿದ್ರು. ಅವಾಗ ಅವ್ರನ್ನ ಹತ್ತಿರದಿಂದ ಗಮನಿಸಿದ್ದೀನಿ. ಒಂದು ಒಳ್ಳೆ ಫಿಸಿಕ್ಸ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಕಟ್ಕೊಟ್ಟು ಹೋಗಿದ್ದಾರೆ ಆ ಕಾಲೇಜ್ಗೆ. ಕೇಳಿಸಿದ್ದೀರಾ ನಿರಂಜನ್ ಸರ್? ಥ್ಯಾಂಕ್ ಯು. ಸೊ ಮತ್ತೆ ಇವತ್ತು ನಾನು ಅವರ ಬಯೋಡೇಟಾ ನೋಡಿದೆ. ಬಹಳ ಸೌಂಡ್ ಆಗಿದೆ ಸರ್, ನಿಮ್ಮ ಅಕಾಡೆಮಿಕ್ ಉದ್ದಕ್ಕೂ ಬಹಳ ಚೆನ್ನಾಗಿದೆ. ಸೊ ನಿಮ್ಮಂಥವರು ನಮ್ಮ ಕಲೆಗೆ ಹೋಗ್ಬಿಟ್ಟು ಇವತ್ತು ನಮ್ಮ ವಿದ್ಯಾರ್ಥಿಗಳ ಒಂದು ಅತ್ಯುತ್ತಮವಾದಂತಹ ಸಂಪದ್ಭರಿತವಾದಂತಹ ಒಂದು ಉಪನ್ಯಾಸವನ್ನು ಕೊಟ್ಟಿದ್ದೀರಾ. ಜೊತೆಗೆ ನ್ಯೂಕ್ಲಿಯರ್ ರೇಡಿಯೇಷನ್ ಕ್ಷೇತ್ರದಲ್ಲಿ ಹೊಸ ಮೆಟೀರಿಯಲ್ಗಳು ಅಥವಾ ನೋವಲ್ ಕಾಂಪೋಸಿಟ್ ಮೆಟೀರಿಯಲ್ ಅಷ್ಟರವಾಗಿ ತುಂಬ ಅಡ್ವಾನ್ಸ್ ಆಗಿರೋದನ್ನ ಹೇಳಿದ್ದೀರಾ. ನಮ್ಮ ಮಕ್ಕಳು ಮತ್ತೆ ಇದನ್ನು ಕೇಳಿಸ್ಕೊಂಡಂಥ ಎಲ್ಲ ಅಧ್ಯಾಪಕರು ಬಹಳ ಪಡ್ಕೊಂಡಿದ್ದಾರೆ ಅಂತ ಅನ್ಕೋತೀನಿ. ಒಂದು ಅತ್ಯುತ್ತಮ ನಡೆದಿದೆ. ಸೊ ಇಂಥ ಒಳ್ಳೆ ಉಪನ್ಯಾಸ ಬಂದಂತ ನಿಮಗೆ ನಾನು ಮನಸಾರೆ ಅಭಿನಂದಿಸ್ತೀನಿ. ಮತ್ತೆ ಹಾಗೆ ಆಗೋದಷ್ಟು ಬೇಗ ನೀವು ನಮ್ಮ ಕಾಲೇಜ್ಗೆ ಆಫ್ಲೈನ್ ಅಲ್ಲಿ ಬಂದು ಇಡೀ ಒಂದಿನ ನಮ್ಮ ಜೊತೆ ಇದ್ದು ನಮ್ಮ ಕಾಲೇಜ್ ಮಕ್ಕಳಿಗೆ ಒಂದು ಒಳ್ಳೆ ಕಾರ್ಯಕ್ರಮ ನಡೆಸ್ಕೊಡ್ತೀನಿ. ಈ ಕಾರ್ಯಕ್ರಮವನ್ನು ನಡೆಸ್ಕೊಳ್ಳಿಕ್ಕೆ ವ್ಯವಸ್ಥೆ ಮಾಡಿದಂತಹ ಫಿಸಿಕ್ಸ್ ವಿಭಾಗದ ನಂದಕುಮಾರ್ ಅವರಿಗೆ, ನಿರಂಜನ್ ಸರ್ ಅವರಿಗೆ, ಇದಕ್ಕೆ ತಾಂತ್ರಿಕ ಸಹಕಾರ ನೀಡಿದ ಸುಂದರೇಶ್ ಸರ್ಗೆ, ಹರ್ಷವರ್ಧನ್ ಸರ್ಗೆ, ಹಾಗೆಯೇ ಎಲ್ಲರೂ ಭಾಗಿಯಾದಂತಹ ಅಧ್ಯಾಪಕರಿಗೆ ಮತ್ತೆ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆಲ್ಲ ವಂದಿಸಿ ನನ್ನ ಅಧ್ಯಕ್ಷ ಭಾಷಣ ಮುಗಿಸ್ತೀನಿ. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Thank you very much, sir, Dinesh sir, for
Good morning to all and all. Myself Harshawardhan CA, Assistant Professor of Mathematics, Government First Grade College Forum, and Vadanasipura. Honorable participants, I feel immense pleasure to propose a vote of thanks behalf of Physics Department, Science Forum, and Government First Grade College of Vadanasipura. I take this opportunity to thank our beloved principal, Dr. Dinesh KS, for his great support to organize this webinar and his encouragement. Thank you, sir. I extend my gratitude to the resource person, Dr. Ishwarappa KM, Associate Professor, Department of Physics, Davangere University. As per my knowledge, Dr. Ishwarappa sir was the first person at Kuvempu University who got the JRF, I think. Sir spared precious time from his busy schedule to grace this occasion and enlighten all of us with innovative ideas and his lecturer. Thank you, sir. Thank you very much.
Thank you very much.
It's my pleasure to thank the man of inspiration, our IQAC coordinator, Dr. Niranjan RS, for his inspiration and constant support to organize this webinar. Thank you, sir. Thank you very much.
Thank you, sir. Thank you.
I would further extend the hearty thanks to the Professor Nandkumar V, HOD of Physics and convener of this webinar, who organized this webinar neatly. Thank you, sir. Thank you very much. Also, I extend my gratitude to the Professor Sundaresh KS, Department of Kannada, for his technical support. Thank you, sir.
Thank you, Harsha, sir.
My deep sense of thanks and appreciation goes to all the participants who are live with us and attended this webinar with great enthusiasm. Made today's event a great success. Thank you, all the participants from different states of the country. Thank you. Finally, I thank all the supporters to this webinar. Thank you one and all.
Thank you, sir, for your speech, vote of thanks, voting vote of thanks. Now I request all the participants to send the feedback form in your group, WhatsApp group. You please, all of you, fill that feedback form and you will get the certificate in 1 or 2 days. Soft copy of the certificate will be sent to your mail ID. And I once again thank Ishwarappa sir for giving your time for this webinar. And I expect the further same cooperation from your side, sir. Thank you very much, and I thank all the participants, and I thank our college principal. I thank all the supported people directly and indirectly. And now it's the time to end the session.
Thank you for the opportunity. I thank all the faculty of the physics department and the mathematics faculty at Shore. And so who is assisting us in Sundaresh sir. Thank you all. Thank you very much. Thank you very much.
Now I request all the participants to left the session. We will close this session.
So shall I leave, Niranjan?
Yes, sir. You can leave now. Sundaresh sir.